Okay, so first of all, thank you very much for the invitation to come here and celebrate Stan. Before I get into my talk, which is try to give you a sense of where neutrino physics is today, I do want to mention just a very quick anecdote. I met Stan when I was a graduate student at Berkeley. And it turned out that at Berkeley, there was a class that all graduate students had to attend that had to do with experimental particle physicists. And I'm a theorist, so I had to do it even though I didn't particularly want to do it. And it turns out that one quarter or one semester that I was there, for some reason, Stan was teaching that class. I don't remember why. I was a graduate student, so nobody told me anything. But he was the one teaching the class. And it turns out that was the class where I learned about neutrino oscillations. Because what we did for the class is we discussed the Minos proposal. And I'm not going to talk about that too much because Jenny's going to talk about it. But one thing I do remember is I have this proposal somewhere, but I couldn't find it. So I asked around for getting a cover of it because it has a very nice cover. And we learned a lot about neutrino oscillations from this. This is before the super K results. So we learned all about what Minos was supposed to do. And I thought it was really, really exciting. It was just around the corner, even though that turned out to be not the case. And I learned lots of things during that time. One thing I learned is that experimentalists have a sense of humor, which is kind of nice. So for example, they don't have a typical person here, but they have this, why is this not working? They have this typical minotaur, just to tell you how big the experiment is. That's actually not easy to do because I don't know how big minotaurs are, but they're about maybe 2.5 meters or something, maybe about this tall. So that gives you a sense of how big the experiment is. One thing which I remember is very exciting about the Minos proposal for some reason to me is that we actually spent a lot of time understanding how they could look for taus. And the tau appearance was going to be really exciting. And one thing that we spend a lot of time talking about is maybe we could put a detector in front of this big chunk of iron, which would be over here somewhere, to have some emotions and some tau detecting scheme so that we can actually do tau appearance. And this was all great. And this, for example, is depicted here in this plot on the right-hand side, which is the sensitivity of the Minos experiment for tau appearance with a 45 GeV beam. And it turned out that this didn't really work out very well. And it's mostly a super K's fault because they ended up picking a value of delta M squared that was actually around here somewhere, which made it really, really hard for the Minos experiment to do tau appearance because they had to go for a beam that was much, much lower energy. And somehow the taus were just too heavy for them. But I remember this was super exciting. And I really got into learning about neutrino oscillations, which turned out to be really convenient for me. So somehow the reason I'm here has something to do with this class that Stan taught at Berkeley for some reason that I can't remember, but it's a very fun class. I want to tell you about how things are with neutrinos today. And after a lot of very exciting couple of decades, we've learned a lot about neutrinos. And again, my job is to give you a sense of where we are today, why we think neutrinos are very exciting, and what we're hoping to learn in the next, let's say, decade or so. That's kind of my job. And people can ask questions at any time, of course. So what we know today is there are at least 3 neutrinos. And we can talk about neutrinos using what's called the flavor bases, electron neutrino, mu neutrino, or tau neutrino. Or we can talk about what we call the mass bases, which is neutrino number 1, neutrino number 2, and neutrino number 3. If you're not in neutrino physics at all, neutrino number 1 has mass M1, neutrino number 2 has mass M2, and neutrino number 3 has mass M3. And the way that these 2 different ways of talking about neutrinos are related is via some unitary 3x3 matrix. And this unitary 3x3 matrix is parameterized by 3 mixing angles, 1 CP odd phase that we can measure in oscillation experiments. And it turns out that in oscillation experiments, and I'll give you a very quick primer of how they work. And again, my pointer is not working. Oh, it is working, but it doesn't work here.
It doesn't reflect off the
See, that's why I was trying to propose this point.
But this was a high order thing, which looked very difficult.
TV has an anti-reflection.
That's can I point all the way up there?
No, but almost here. Those are all.
Okay, so you can plug it in and I will make a fool of myself.
I try, yeah, so there's
you
only,
plug it in?
yeah, you get the cursor because.
Okay, that's fine. So I will move to this side where I can see something. Okay, so, oh, I see. That one even looks different. So the way that neutrino oscillations work, and I will just say this very briefly for people who've never thought about this, is that you produce a neutrino in a specific flavor, and that's a linear combination of the Hamiltonian eigenstates, the nu1, nu2, and the nu3. So as the neutrino propagates in time or in space, it propagates not as an eigenstate of the Hamiltonian, but as a mixed system, and those relative coefficients of the different amplitudes that you have will change, and then you can change from one flavor to the other. And that thing's, yes?
So you're saying the eigenstates of B1, B2, and B3 correspond to M1, M2, and M3 respectively?
Good. So we can talk about that. So basically what happens is you produce an electron neutrino, and the electron neutrino is a linear superposition of states with different masses. And then as those states evolve in space and time, each one of those different components acquire a slightly different phase. So at the end of the day, when you make a measurement of the flavor of this in either, let's say, the muon state or the tau state, you don't have the same state that you had to begin with. So there's a non-zero probability for that to be measured as a separate flavor. The reason I'm mentioning this very briefly is to say that this phenomenon is a sinusoidal-like phenomenon, so it oscillates. And the frequency of the oscillation is proportional to what makes the nu1 different from the nu2, different from the nu3, which is related to their masses. And in reality, what we end up measuring is the differences of the neutrino masses squared. So that means as far as oscillations are concerned, what I care about are the coefficients of this matrix. And I also care about the differences of the neutrino masses squared. So we have 3 neutrinos, we can define 3 masses squared, and we can define 2 different differences of masses squared. That even sounded right. So that's what makes up neutrino physics today, and our job is to characterize what the system looks like. And we've made a ridiculous amount of progress since I took that class in 1996 or 1997. And we've actually been able to measure all of these neutrino mixing parameters, sometimes ridiculously well. You know, ridiculously well, even at the 3% level. Did I do? I could speak with the voice of voiceover actor. That is definitely new. That would be a very subtle earthquake warning. I wouldn't do it that way.
Somebody's phone. That's cool.
Is it a phone?
It's my phone that rings that way.
Is it your phone?
No.
Somebody's phone.
Stand for switchboard.
Okay.
You know it.
We're back. So the point is we have all of these different new parameters in the neutrino sector, and we'd actually be able to measure those at the few percent level, with a couple of exceptions, which I'll show in just a minute. One is we don't know whether CP invariance is violated in the neutrino sector, and we also don't know how the neutrino masses are ordered. And I'll show you a picture of that, especially for people who've never heard about this before. So these are kind of the big, obvious questions that we're asking, is we need to understand whether CP is a good symmetry in the lepton sector, and we need to understand how the neutrino masses are ordered. And these are all things that we can learn with oscillation experiments. I want to make a pause, and I want to try to tell you why theorists care about neutrinos. And it has nothing to do with those numbers that I was showing you before. Okay, the reason people like me care about neutrinos is that they have mass. But they have a really, really tiny mass. And this is something which I think is useful for non-particle physics people to kind of appreciate. So this plot here on the left-hand side is a convenient plot with all of the masses of the fundamental fermions in particle physics. Again, if you're in particle physics, you've seen plots like this before, or maybe you don't even make a plot out of this before. So you're accustomed to this concept that all different particles have different types of masses. But I always want to highlight, especially for the non-physics people, that this is a really, really crazy plot. Okay, these are all fundamental particles. So they're all the fundamental building blocks of matter. And if you forget about the neutrinos, the masses of those things can span 5 orders of magnitude, a factor of 1 million or 100 million. Did I say that right? That sounded right. Okay. 100,000, thank you. Yeah, I was more accustomed to the neutrinos. So that's already kind of a mystery, is to understand why these guys span so many orders of magnitude. Yes?
Okay, wait, sorry, what is the x-axis is fermion?
It doesn't mean anything. It's just a way of spreading them out so that they don't all line up. That's a good question. Yeah. If you want, it doesn't even work, so don't worry about it. So, but this is just to say, these are all the particles these are all the masses of the fermions that we know about. And there's another fun thing about this plot for people who like a history of particle physics is this also shows us why it was very exciting to be building new accelerators with slightly higher energies as time went by. As we built an accelerator, we got into like over here, and then a little bit better, we start to see some new particles. We build a little bit more, we see some more new particles. We build a little bit more, we see some more new particles, and then we ran out of new particles. But that's where the charged fermions live. And the neutrino masses that we have found are actually all the way down at the bottom of the plot. And one thing which I like to remind people is if you're very confused about the fact that the electron is 10 to the 5 times lighter than the top quark, and these are the lightest charged things that we know about, the neutrinos are way lighter than that, and the gap is bigger. So the gap between the largest possible neutrino mass that we can allow with all the data that we know today and the electron mass, that gap is at least an order of magnitude bigger than the gap between the electron mass and the top quark mass. There's another fact which is highlighted here, which is this region in green or blue, is that there aren't any particles there. So there's really a big gap. If you look between the electron and the top quark, there's a whole bunch of particles in between that make life exciting. And here in this void, there really aren't any particles that we know about. So the neutrino masses are non-zero, but they look strange and different. And that's what we get excited about. And of course, the thing that we're most excited about, or at least that I'm most excited about, is that we don't know how to explain neutrino masses. We need some new stuff in order to explain how neutrinos have a mass that's not zero. It's kind of what I wrote down here, is that from the point of view of the way that we think about modern particle physics today, in order for you to explain neutrino masses, you need to add some new fields into your system. So you need some new particles. So in some ways, neutrino masses imply the existence of some new particle. What makes life exciting, or maybe scary, is the fact that we know almost nothing about what these new particles are. They could be bosons or fermions. They could be really light, or they could be ridiculously heavy. They could be charged. They could be neutral. They could be some new particle that we'll find tomorrow in some experiment, or they could be some new particle that's almost impossible to find in any experiment. And that's what we know about this new physics that's lurking around in our neutrino masses. What I have down here at the bottom of the slide is a description of the other stuff in fundamental particle physics that we don't know. And we're still trying to sort out electroweak symmetry breaking. That's related to the Higgs boson. That seems to be very standard model-like, which somehow is surprising, at least to lots of people. There's this thing called the dark matter that we don't know anything about. There's this thing that the universe has too much stuff in it. That's a good thing, but we don't know how that happened. And then there's this really, really weird thing that somehow the expansion rate of the universe is accelerating. And somehow that's a particle physics question. And if it is a particle physics question, we have no idea what the answer is. So these are the things we don't know. And if you look at the experimental particle physics program today, it's aimed at addressing subsets of these questions. And neutrinos are one of these really big questions that we would like to get answers to. So let me say something about neutrino masses for the particle physics people, or for people who've heard enough about particle physics to care. And masses are always annoying in particle physics. All masses come from the Higgs mechanism. That's what we learn in graduate school. And neutrinos are not an exception. Their masses have to have something to do with electroweak symmetry breaking. So that's not negotiable. Neutrinos are part of the standard model. Their masses have something to do with the Higgs boson. What makes neutrinos interesting is that you have some non-trivial choices, and we don't know which one of these choices is the one that nature made. One possibility is that neutrino masses talk to the Higgs boson just like everybody else. If that's the case, we need to have what are called the right-handed neutrino fields in the theory. And on top of that, we need to understand, if you want, why the neutrinos don't talk too much to the Higgs boson, but only a tiny bit. And we also need to understand why somehow lepton number is conserved. And I'm not going to talk more about that. Yes.
So what? Because we're talking about the neutrino masses. When was it? When were you guys able to discover that like neutrinos actually have mass, or like they'd have this like the invariable mass, or
Yeah.
not the rest mass?
So we learned about neutrino masses 25 years ago, at least beyond reasonable doubt. If you care, if you like to live with reasonable doubt, we've had evidence for non-zero neutrino masses since the late 60s or the mid 60s from the solar neutrino problem. But we only got definitive, beyond reasonable doubt evidence towards the end of the last century. So 1998 is usually assumed to be the moment in time when we learned that neutrino masses were not zero from the supercamiocondic.
I see. And then you just tried to actually find the number.
We haven't gotten there yet. We don't know what the number is. There's one of these curses of particle physics or neutrino physics. We can only measure the differences of the masses with oscillations, but we don't know what the masses themselves are. So we're still working on that. That's an interesting, very hard experimental problem. But people are making progress slowly. Okay, so coming back to neutrinos, like I said, one possibility is that the neutrinos talk to the Higgs boson just like everybody else. Another possibility is that maybe the neutrinos talk to a different Higgs boson, and that explains why their masses are weird. And then a third possibility is that the neutrinos talk to the Higgs boson, but they also talk to some other source of mass that's lurking out there, and that the neutrino masses are the combination of those two different sources of mass. And this is the more complicated possibility, and it is, of course, the one that everybody likes. So if you ask around, that's the one everybody's willing to bet on. But of course, these are not philosophical questions, but they're experimental questions, and we need to learn what the answers are. So there's a lot of experiments that we need to do in order to figure out how neutrino masses are happening. This is just a cartoon of the different possibilities for the new physics scale that might be lurking out there that might have something to do with the neutrino masses. And as I promised, it goes all the way from a sub-electron volt scale all the way to the ZeV scale or the gut scale and everything in between. And what's sort of highlighted there is a distribution of different kinds of places where you would hope to see this physics that might be responsible for neutrino masses. And this is just to give you a sense of how diverse the possibilities are. So if we want to piece this neutrino mass puzzle, we have to be looking for new physics in lots and lots of different ways and in lots and lots of different places. So I'll talk about some of this, but you see that this involves things like neutrino experiments, charged lepton experiments, collider experiments, astrophysics experiments, and cosmology. So these are all of the different places where we hope we'll get to learn something about the origin of non-zero neutrino masses. I want to say something very brief for people who are a little bit more in the know. A really big question about neutrinos that may be a big hint as to where their masses come from is whether the neutrino is a Dirac fermion or if it's a Majorana fermion. If you don't know what that means, I don't have time to talk about it, but I'm happy to talk about it afterwards.
So is that right thing a real statement? Like you've run this,
I have not run the experiment,
okay.
But I have selected data informally, as in chatting to people in the coffee break. I am willing to believe that that's artistically correct.
Very short.
Oh, that's a great question. It is not, and we can talk about that because I'm very excited about that. But we're not going to talk about that here. It's a pretty good fork.
Yeah.
And
You can follow Yogi Berra and say,
yeah, if you see a fork on the road, take it. Yeah, it's a good picture too. So I like that picture. So, but this is a really big question that we have today, and it drives a big chunk of our experimental program, which is searches for neutrinoless double beta decay, which I don't want to talk about because I want to talk a little bit more about oscillations. But there's a big industry, and Georgia's part of the industry, to actually look for neutrinoless double beta decay, which is a way of looking for the very violations of lepton number. And if we decide that lepton number is not a good symmetry of nature, then we learn almost for sure that neutrinos are Majorana fermions. And that would be a great way of making progress towards understanding where neutrino masses could be coming from. It's a very exciting enterprise because even if you don't see anything, you actually learn something. So it's one of these rare process experiments where if you see something, it's very exciting. If you don't see something, it's disappointing, but you also learn something along the way. And these experiments are very hard, and I'm not going to be talking about that. Now, in the business of learning about neutrino masses, it is always important to step back and remind yourself of the fact that we've never, ever, ever seen evidence for a non-zero neutrino mass outside of an oscillation experiment. That's just a fact of life. Neutrino masses are really, really tiny. And we've looked for consequences of them in lots of other places, and they've only shown up in oscillation experiments. And again, we've tried. Like Fermi wrote a paper in the 1930s telling us how we were going to find neutrino masses by studying beta decay. We've been doing that for 90 years. And we're getting really good at it, but we still haven't seen evidence for a non-zero neutrino mass. So it stands to reason. So first of all, oscillation experiments are amazing because they can see this really, really tiny effect, which we don't appreciate enough, I suspect. And the other thing is, if you want to learn about neutrino masses, it may not be such a bad idea to look at the only one place we've ever actually seen non-zero neutrino masses. So does that mean we're going to learn about neutrino masses by doing oscillation experiments? I don't know, because this is science, right? But it looks like a good idea. And of course, we have a lot of very large projects associated to non-zero, to doing oscillation experiments. There are a couple of big ongoing experiments in Japan and in the US. There's a very big project that's being built in China that's supposed to start taking data next year, I hope. That's called the Juno experiment. There are experiments in the South Pole, these gigantic ice cube-like experiments. And then we have two very big projects being built in the US and also in Japan to study neutrino oscillations in a lot of detail. 10 minutes, perfect. So I will say something about what these experiments are for, and I think that's mostly what I'll be talking about. Okay, so let's go back to talking about oscillations and neutrino masses. So what's depicted here on the left-hand side is how the neutrino masses M1, M2, and M3 are ordered. And there are two possibilities. Okay, and that's the information that we have access to. The other thing that's depicted here in the colors are the elements of the neutrino mixing matrix. So the fraction of these different bars that are colored in a certain color represent the element of the mixing matrix absolute value squared. And what's listed on the right-hand side are the things we still don't know about neutrino mixing. So we don't know whether CP is violated. I've talked about that. There's another funny question that we like to ask, which is if you look at these pictures here, and you look at the green bars relative to the blue bars, the green bars and the blue bars all have the same size. And you can ask, why is that? The reason is because I drew it that way. But it's also allowed by experiment. And the question we want to know is that really true, or is the amount of green and blue not the same in all of the different states? And that's a question that some theorists care about, and it sounds like a good question to be asking. And of course, there are two pictures there, one on the left-hand side, one on the right-hand side. Only one of those is true, and we would like to know which one is true, or which one is correct. The one on the left-hand side is called the normal mass ordering. The one on the right-hand side is called the inverted mass ordering, and we would like to know which one is correct. Now, when you hear about neutrino oscillation experiments, you will hear that that's what people are trying to measure. And then they'll tell you how well they can measure these things, or how well they can distinguish one mass ordering from the other mass ordering. And for some people, that sounds kind of boring. We're just measuring a bunch of numbers, and why the hell are we doing that? But I want to remind you that that's not why we're doing these experiments. The reason we're doing these experiments is that even though we've constructed this really nice picture, we don't know if that's the right picture. It's just a picture that works. So our job is not to just measure a bunch of numbers. If you want, our job is to measure these bunch of numbers in lots of different ways and see if you always get the same answer. So our job is to test the formalism and not just to see that the values that the numbers have. So let me remind people of this. If you don't know what it is, don't worry about it. If you do know what it is, these are measurements of mixing in the quark sector. And each one of these colors is a different measurement of the same two parameters, rho and eta. This took a really long time to accomplish, and my plot is old. This is from like 2009. If you look at 2019 version of that, it looks exactly the same, but the error bars are smaller. So, and you notice that, again, every color here is a different measurement. And you notice that we've made a lot of measurements of these two parameters, which feels like a waste of resources, right? I mean, it's two parameters. If I make two measurements, I should be able to measure those things and be done with it. But the reason we were doing it was to make sure that every time we made a different measurement of the same two parameters, we got the same answer. So we want to make sure that all these curves agree at the same point. And if they don't, that means that we're missing something. That means that our formalism is wrong. Sadly, it turns out, in the quark sector, they all meet at a point that lives right over here, which is kind of amazing. And if you make the error bar smaller, they also meet at a point that just looks a little bit smaller. So what we would like to do is the same thing in the lepton sector. And if we go back to neutrino experiments in the neutrino mixing matrix, I told you that we've measured all these mixing parameters very well, but that's actually cheating a little bit because we make some hypotheses in order to measure those parameters at the few percent level. If you ask what we've actually really measured is mostly the absolute value squares of the parameters that live in the top row and in the last column. That's what we've measured. It's just the absolute value squares of these things. And that's it. So we have a long way to go to start asking more detailed questions about even this matrix. You know, is it a unitary matrix? And does interesting things happen? So we have a long way to go. And just to give you a sense of the equivalent of that unitarity triangle in the neutrino sector, this is a very big plot. But basically, where we live, these are two different unitarity triangles. So just look at your favorite one, either on the left or on the right. And where we are today, if you take all of the data, and even if you assume unitarity, you have to be somewhere in the green region. So you see that it's kind of a triangle that can live anywhere in space. And if you allow for unitarity violation, the triangle gets a little, these moons get bigger. In the future, we're hoping to get to these a lot smaller regions, which looks much more exciting as far as making a measurement is concerned. But on top of that, if you start asking weird questions, you might end up learning something that's exciting, which is you might end up in a situation where if the hypothesis that you're making is incorrect, your experiments have the ability to reveal that. 5 minutes, yeah. So I'm going to skip some things. So this here is a cartoon of what would happen if you were measuring a bunch of different things in Dune and Diabet and in a theta hyper K. And if somehow your mixing matrix was not unitary. Again, remember that the name of the game is to measure the same things lots of times and ask if there's a point in this parameter space where everything meets. And you notice that in this picture here, there's no point in the parameter space where all the curves meet. So that means that it is possible 10 years from now that we will be in a situation where we've made all these oscillation experiments and the picture that we have constructed doesn't hold water. There's something missing. And that would be a very exciting. And that's part of the reason why we're doing these very big, very ambitious oscillation experiments. I'm going to skip this. We like to talk about CP violation. So let me say a few words about that. CP violation is one of those weird things that can happen in nature, but it doesn't have to happen. And it turns out that it does happen in the quark sector. So that's something that's already known. And what's interesting is in the quark sector, and this is kind of exciting, all of CP violating phenomena are governed by one number. So if you could build a different universe where you had a different value of the CKM phase, the amount of CP violation would change altogether, okay? And if you turned it off, then all CP violation in the quark sector would go away. It turns out that this didn't have to be true because there's another CP violating observable in the Lagrangian. which is this infamous theta parameter in the QCD Lagrangian. That number is an angle, could be anything from 0 to 2 pi. And as far as we can tell, that number is exactly 0. Again, there's no such thing as exactly 0, but it's known to be less than like 10 to minus 10 or 10 to minus 11. So it's really, really ridiculously small. By the way, the CKM phase is about, I'll say it wrong, 70 degrees. Some big random number that you could just have pulled out of a hat. So that means in the quark sector, the two CP violating parameters, one is less than 10 to minus 10, and the other one is 70 degrees. In comes the neutrino sector. The neutrino sector can have 3 different CP violating parameters. That's way more than 2. So if you want to learn about CP violation, neutrinos are the place to be. And remember, in the quark sector, one parameter is less than 10 to minus 10. The other one is 70 degrees. So what do you think it's going to be in the neutrino sector? Before you make your guess, I want to remind people who are more senior than me that at some point people asked about the possibility that maybe the neutrinos mix, and what would those mixing angles be? And people said, well, you know, mixing angles in the quark sector are kind of small. So these neutrino mixing angles are probably kind of small, which, by the way, is why nobody believed the atmospheric neutrino anomaly, because it needed large mixing angles, which is clearly wrong, except that it's not wrong. Okay, so if you have your favorite guess about how much CP is violated in the lepton sector, it seems wise to hold your guess to yourself and actually do the experiment and find out what the answer is. Okay, so I have very little time, so I'm going to skip things that, well, actually, I'll just talk about this slide and I'll skip the other things. So you could ask yourself, okay, so I'm telling you we have to check that the formalism that we've constructed is correct. Now, if it's not correct, what could we be missing? And the answer is there are lots of different possibilities. So this is a list of the more boring ones. One is that maybe there are more neutrino states than we think about. That's not just a random thing you can think about, but there are many models that explain non-zero neutrino masses that require new neutrino states. Maybe the neutrinos have some new interactions that we don't know about. And again, you could say, why would the neutrinos do that and not everybody else? And the reason is neutrinos interact very weakly. So they are always at the mercy of a new interaction a little bit more than everybody else, because they can be, and oscillations are very particular about how neutrinos interact and how that gets felt in the oscillation. Neutrinos can have some weird or not so weird properties. For example, the neutrinos can have a finite lifetime. The neutrinos can have a non-zero electromagnetic moment. And it turns out that we know for sure that the neutrinos do have a finite lifetime because they must, because that's what the standard model tells us. The lifetime is like 10 to 40 years if you believe in weak interactions, but it's not zero, not infinite. And the neutrinos must have a non-zero dipole moment because they have mass. But those numbers in the standard model are expected to be super tiny. But if they're not super tiny, they could show up in oscillation experiments. And of course, oscillations are weird. So they're sensitive to very weird small effects that I'm not going to talk about, like maybe quantum mechanics is wrong. Maybe Lorentz invariance is violated in some subtle way, or whatever favorite weird stuff you like to think about. CPT violation, we don't care about that. But these are different things that we could run into. And this, of course, is only restricted by the imagination of theorists. So just keep that in mind. Okay, so the last thing I'll say is that neutrino oscillation experiments are also great places to do other kinds of physics searches, which I'm not going to talk about. But basically, what we're doing in neutrino oscillations is we take a proton, Jenny's going to talk about this. You take a proton beam, you hit it on a target, you produce a bunch of stuff, including neutrinos, and you want to measure that stuff nearby. So if you're producing weird stuff along the way, that weird stuff can do exciting things for you. And I'm going to skip that. So let me conclude, because I think I'm out of time. Again, what's time? We started in a very confusing way. Okay, so let me just conclude very, very briefly about where we are with neutrino physics. So I think the main message is we know that we've run into something exciting with non-zero neutrino masses, but we still know very little about what that physics is. We know neutrino masses are very small. We don't know what that means, but it feels like something important. I didn't talk about this, but neutrino mixing is also very different from quark mixing. We also don't know what that means, but it also feels like it could be something important. We are in a place where we need more experimental data. So we're in a sort of a data-starved era and not in a data-rich era. So in order to make progress, we're going to need different new experiments. I mentioned a little bit about next generation oscillation experiments and what they're going to be teaching us. And there are all different kinds of experiments that will also inform non-zero neutrino masses. The last thing I want to say, which I've already said, but it's always useful to remind you, is neutrino oscillation experiments are very interesting kinds of experiments. They're also very, very unique. They don't look like regular particle physics experiments, but they're unique in the sense, and this is very important, they are the only place where we could see non-zero neutrino masses. Now, why is that? It's because of the magic of quantum mechanics, right? It's because of quantum mechanical interference that we can have a super tiny effect that if we're patient and if we can wait long enough, that phase can, in quotes, pick up. And then you can get a very big non-trivial effect. So we have this gigantic, ridiculous quantum interference device that has a baseline of 1,000 kilometers in the more absurd case. And somehow quantum coherence is maintained, which I always find sort of mind-boggling. And because we're doing a very, very precise quantum interference experiment, we are sensitive to lots of interesting, unusual things that we may not have thought about. But I think it's always important to keep that in mind when we're talking about a neutrino oscillation experiment, because something exciting could happen. And we haven't been wrong about that, at least for the last 20 years or so. So I'll stop and take questions. Thank you.
Questions, comments, for either Georgia or Andre? Go ahead.
Okay, so I just wanted to elaborate on a couple of things that Andre said. The first is for non-experts, the other one for experts. Maybe. The one for non-experts is that the reason why oscillations are so good at, they're so powerful is the same reason why your piano tuner plays two notes at the same time. And by hearing the beats between, that is the frequency difference, you can actually detect tiny differences between the two notes, and then can go ahead and tune the piano. Now, these days, they have a frequency meter, so they don't probably do the same. But I mean, the classic piano tuner used to use essentially oscillations, not quantum acoustic oscillations.
Orchestra tunes.
Orchestras, yeah, that's right. Your cello is tuned the same way, right? Versus the other thing is that I wanted to actually, so you mentioned that the mixing sometimes, there's surprises, and the quark mixing is very small. It turns out that, in the neutrino sector, those are large numbers.
Yeah.
Camland almost did not get approved or funded in the US because, quote unquote, this is DOE, well, everybody knows that anyway, they're not going to see anything because they only sensitive to large mixing angles. So,
yeah. And again, this is, there are two mixing matrices in nature. This is the quark mixing matrix. Of course, the numbers are drawn in a way that calls attention to how big or small they are. And this is the neutrino mixing matrix. And they clearly look very different. And what I like to ask people is, which one looks weird? And I bet it's not the neutrino one. This one looks pretty weird. Why would nature choose that? This doesn't look very weird. So maybe we're asking the question in some upside down way. Yeah.
The neutrino is also the most numerous standard model particle in the universe, and you didn't speak to the role of cosmology. Now that we're getting into an era of precision cosmological experiments, maybe you could say a few words about how
absolutely.
Cosmology can
so
tell us about neutrino.
So this is something I skipped altogether, and it's very important. So if you look at the composition of the universe today, the universe is mostly made out of photons. We don't care about those. The matter particle that's most heavily occupying the universe are neutrinos, almost the same number as the photons. That means that if you compare the number of neutrinos in the universe to the number of let's say, protons, which is kind of dear to us because we're made out of those, it's about 10 billion to 1. So there are 10 billion neutrinos for one regular kind of particle that we're familiar with in the universe as a whole. On the other hand, we barely know that those neutrinos exist, but we have a lot of indirect evidence that they do exist. And what happens is because there's so many of them, they impact the evolution of the universe in a very non-trivial way. So by measuring how the universe is evolving as a function of time, because the neutrinos have been around since almost the beginning of time, they have a huge impact on how the universe evolves. And that's how we learn that the neutrinos are there, because if you take them out of the equation, the numbers don't close. And it also gives us an opportunity to learn about the neutrinos themselves by making very precise measurements of how the universe is evolving. So for example, if the neutrino has a tiny mass, for most of the history of the universe couldn't care less that it has a non-zero mass. But because the neutrinos today are cold, at some point, the universe got to start caring about the fact that the neutrino masses are not zero. So the non-zero neutrino masses leave an imprint somewhere in the structure of the universe. And it's mostly felt in how the galaxies are distributed in space. So if you look at the distribution of galaxies in space, and if we understand the dynamics of that, the mass of the neutrino plays a role in telling you how many galaxies of a certain size you have in the universe in a certain direction. So that's sort of a very exciting place to be today, is because we're making precise enough cosmology measurements that if we believe the model, we can learn about the neutrino properties themselves. There's a totally different story, which is you can say, I don't care about these model people, and I don't believe any of those things. Can we see those damn neutrinos that are here in this room in big numbers? And the answer is we don't know how to do that, but we're working on it. We have lots of bad ideas of how to do it. We have a few ideas that have not been proven to be bad yet. So we're exploring those, and people are very excited. And it is the sort of thing that if you are my age, you will not get to see in your lifetime a discovery of this cosmic neutrino background, probably. Although I plan to live forever, but that's just a plan. But if you're young, it's one of those things that sounds very exciting. So a measurement of this neutrino background is not only a cool thing to do, but in the ultimate long run, it contains a lot of information about how the universe looked like a very long time ago. And that's information we can't really get to in almost any other way. Yes.
Oh, I was just gonna ask, when you were talking about the CP violation before, wouldn't that imply that, like, wouldn't the CP violation imply that neutrinos are Dirac fermions?
That's a good question, and the answer is no. So, and yeah, so when we do these CP violating experiments, the question we're really asking only has the neutrino as an intermediary in the story. So let me
not that it's then visible.
Well, no, but basically what happens is when we do the experiment with oscillations, we have two kinds of neutrinos. There's one that's left-handed in helicity, so you can label it by how its spin is projected.
A half spin?
Yeah, the spin is a half, but the spin is always projected in a way that we say is left-handed. So let's just go with that for the language. And then there's another experiment we can do where the neutrino is right-handed. As far as any experiment is concerned that we can conceive of doing, the left-handed neutrino always behaves like the thing that we call a neutrino if the neutrino were Dirac. And the right-handed neutrino always behaves like the thing that we call the anti-neutrino if the neutrino were a Dirac fermion. If the neutrino is a Majorana fermion, there will be a left-handed thing and a right-handed thing, and you can call them whatever you want, but the stuff that the left-handed neutrino does, whether the neutrino is Majorana or Dirac, and the stuff that the right-handed neutrino does, whether the neutrino is Majorana or Dirac, are the same. So as far as your experiment is concerned, it doesn't matter if they're Majorana or Dirac. What they're doing in an oscillation experiment is always the same as if they were Dirac fermions.
Okay.
And that's that didn't come across as well as it could have, but that's the idea. So it's a great question that people often ask, including grown-up physicists. And it's something that Majorana versus Dirac is very confusing, especially if you think about it for the wrong amount of time.
What's the right amount?
It's either 0 or a very, very long time. So if you don't think about it, you will be right 99.9% of the time. So if you just say, I don't care, that's good enough because most experiments don't care. Except you build the experiment that does care, but these are very difficult experiments.
But like, how can it be both in for the same? Is it that for like other fermions?
Yes, it would be.
Oh,
So it's just that you have to ask yourself, what does a Majorana neutrino do that's different from a Dirac neutrino? And the answer is the Majorana versus Dirac neutrinos, they do almost always exactly the same thing in a way that you can't tell whether it's one or the other, except for some very special rare circumstances where you need to build an experiment that's designed just to answer that question. So for most things, you can't get an answer to the question.
And that's because the mass is so small.
That's exactly
smaller,
right.
There's a theorem that says that the smaller that mass is, the more indistinguishable the two cases are.
Yeah, exactly. Yeah.
So that's
Good.
Andre, just a quick comment on your
Yes.
CKM unitarity triangle, which is not what your talk is about, but
Yeah, but that's a
but
good
since
point.
you showed it, I just point out, while, taken as is,
Mhm.
everything looks consistent, okay? It is sort of puzzling why that triangle, it looks so much like a right triangle, why that angle is 90 degrees in that corner. That is a mystery.
Absolutely.
And the second thing I'll point out is, there's still enough wiggle room, for example, in VUB and VCB, that, there could be a fourth little corner, in terms of closure of that triangle, there could be a tiny little side that we don't know about yet. And that's still, an open.
Absolutely, yeah. So I did not mean to imply that pursuing flavor physics in the quark sector is not a worthwhile investment. I just wanted to highlight the fact that it is an investment that we've been making for a long time. And a good way of thinking about where neutrino physics might be going is we would like to be able to do stuff like that.
Yeah, of course.
Of course, in the neutrino sector, the challenge is that we don't have a lot of observables.
Right.
So if we wanted to come up with a dozen observables, we wouldn't be able to, because just there aren't. But we work with what we have. But basically, it's just to illustrate that it is a great way of looking for new phenomena to do these consistency checks of your model. And there's existence proof that we've been doing that very successfully for quite a long time, since the B quark was discovered in the 70s or something. But I did not mean to imply that the game is over. It's just that it's a game that's been played for quite a long time, and we've learned a lot, but we haven't broken the triangle yet. And there's still questions that we don't know how to answer. That is correct. Yes. We don't know why it's a triangle at all. It could have been collapsed, but we don't know.
More questions or comments? If not,
Dave had a
Can I
question.
just ask one? Didn't want to extend it too long, but between the normal and inverted hierarchy, besides knowing what they are and the implications that that's going to have for searches for things and sensitivities to double beta decay and neutrino mass and so on and so forth, is there immediately a deeper piece of physics that would imply?
Yeah, that's a very good
one
question.
over the other.
Yeah, so I'll just say what I normally say when people ask that question. So this here is called the normal ordering. This is called the inverted ordering. And the way this one is called normal is because if this mass is relatively small relative to the other two, then this is just like how all the other particles are ordered. So the electron, the muon, and the tau are ordered in a way that the electron mass is a lot smaller than the muon mass, which is a lot smaller than the tau mass. And the same thing goes for the quarks. So if the neutrino mass ordering is normal, that is one bit of information that you learn. If it's inverted, what's very interesting is the fact that in that scenario, no matter what the mass of the lightest state is, those two state, and again, this is an M square plot. If you make an M plot, the reason we make an M square plot is because if you make an M plot, the way the plot looks depends on what the masses themselves are. But even in this inverted ordering, it is guaranteed that M1 and M2 are almost exactly degenerate in mass. That sounds interesting, if nothing else. And again, you can say, what does that mean? The answer is, of course, we don't know. But we have, I'll mention some bad parallels, but they are sometimes constructive. So when people were learning about mesons, we learned that there's a pi plus and a pi zero. Their mass is almost exactly the same. And we know that turns out to be a big deal. The proton and the neutron mass are almost exactly the same. The K plus and the K short masses, or the K plus and the K long masses, are almost exactly the same. And all of those things we understand. We're not surprised by the fact that they're almost exactly the same. So if those two neutrino masses are almost exactly the same, it's almost inviting us to speculate that there's a good, deep reason that explains why two things are almost exactly. It wouldn't have happened by chance that two masses are almost, and this is at the percent level degenerate. It's not 10% or 20%. It's almost exactly the same, really. And that feels like it's very important. And if you're in the business of building models, it is one thing people would latch on to say, I need to understand why nature would do that, and that would be indication of some internal symmetry that might be telling you that this is what's going on. That's what the theorists would say. And I bet that would be important. So
we should take this conversation with coffee. Thank you, Andre.